So let's talk about gases in just a little bit more detail. So a quick review, because we're going to reference it a lot. STP means standard temperature and pressure. Standard pressure is 1 atmosphere or 760 millimeters of mercury. Standard temperature is 273 Kelvin or 0 degrees Celsius. So those are just some factors or some facts that we're going to need to keep in mind. So we learned from the molar volume of a gas exploration that for all gases at STP, they occupy a volume of 22.4 liters. So you remember Avogadro from last semester, we talked about him a lot. He said that if pressure, volume, and temperature are all equal, the number of particles, or the N, must be equal. So likewise, in this case, if pressure, N, our number of moles, and temperature are all equal, so P and T are taken care of with STP, N, because we're looking at 1 mole of a gas, the volume must be equal. So the volume of any gas, it doesn't matter what kind, at STP is always 22.4 liters. So let's review our relationships between pressure and our 3 variables. So pressure and volume have an inverse relationship. So if pressure goes up, volume goes down. Pressure and the number of particles or the number of moles have a direct relationship, and pressure and temperature also have a direct relationship. If we were to combine all of these together, we'd say that pressure is proportional to N times T divided by V. Because it's proportional to N and it's proportional to T, and it's proportional to 1 over V. So we've just combined all of these into 1. If we rearrange this, we can say that pressure times volume is proportional to the number of moles times temperature. If we want to make this look like an actual equation, we can put an equal sign in here. In order to do that, though, you need a constant. So we have P times V equals N times T, and we have R. R is our gas constant. That's going to be a specific number that's going to depend on what units we're working in, but we'll always work with the same kinds of units. And we'll talk about that in a second. This equation is called the ideal gas law. You'll hear it pronounced often as Puvnert or Pivnert. I usually say Puvnert. That's just some way to actually make this equation into a word, but it's just pressure times volume is equal to the number of moles times the gas constant times temperature. If you didn't follow the derivation, that's fine. This is what you should highlight in your notes. So let's look at that gas constant. Now, in our equation, we have pressure, volume, number of moles, and temperature. If we take those at STP, we have a number for each of those variables. Pressure would be 1 atmosphere, volume would be 22.4 liters, our N would be 1, and our temperature would be 273. If we rearrange this to try and solve for our constant, and we plug everything in, we end up with a number that's 0.0821 liter atmospheres per Kelvin mole. So that incorporates each of these units. So that's why our units are very specific. In order to use this number, your units for pressure have to be in atmospheres, volume has to be in liters, moles are always moles, but we're not going to do like micromoles or millimoles or anything like that, just moles, and our temperature has to be in Kelvin. Otherwise, our units won't cancel and our constant won't work. So this is the gas law constant, 0.0821 liter atmospheres per Kelvin mole. We called this the ideal gas equation, but what exactly is an ideal gas? An ideal gas is something that very specifically and very exactly follows each tenet of kinetic molecular theory. We talked about that way back in Unit 2. It dealt with how the gas particles moved, how they interacted or didn't interact with each other, and it all dealt with the kinetic energy. So we can say that it's a gas that perfectly follows kinetic molecular theory. It exists at high temperatures and low pressures. An ideal gas, the ideal gas law, so that particular relationship falls apart and doesn't work at low temperature and high pressure. We'll assume that all of our conditions follow the ideal gas law or work with the ideal gas law. But I just wanted you to know that not everything is considered an ideal gas. And maybe later in your chemistry career, you'll figure out how to account for that and what equations you need to use for real gases or non-ideal gases.